Today we're going to finish Green's theorem. We're going to do some applications thereof. This is a very long section. First application is to line integrals that are not closed curves, right? We said we wanted a closed curve to apply Green's theorem before, but suppose we have this integral along C like that. How can we evaluate it? It's a pretty tough integral because suppose I wanted to do this, integral of sine x plus y dx plus 6x plus y dy. That's pretty complicated to do by our other theorems. However, if I notice that the line integral along the y-axis is actually pretty easy to compute, I realize that the line integral along C that I want is the same as the line integral along here, subtract this part. Or equivalently, line integral all the way around, add going backwards. So that's what I'm going to do to evaluate the line integral along C of this complicated function. By the way, this is an integral f dot dr. Remember, this is the little f dx plus little g dy, or f1 dx plus f2 dy, depending on your textbook. This is an integral f dot dr, just in the other notation. So what we do is we look at this and we say this is f1, the first component of f, or little f. This is f2, or little g, the second component of the vector field f, in Green's theorem for line integrals. Right? So what I'll do then is say the integral f dot dr that I want along C is equal to the integral all the way around. Add this integral backwards along C1. C1 isn't labeled here, it's going up this way. So, and this one going back this way will cancel the one going this way, right, because it's minus this part. So what we have then is the integral along around the whole half, the red part, C hat here, is, by Green's theorem, the double integral df2 dx minus df1 dy, or dg dx minus df dy we wrote last time. And let's see, df2 dx is derivative of 6x plus y with respect to x is 6. df1 dy is derivative of sine kx plus y, sine x plus y with respect to y is 1. So it's just 6 minus 1 is 5. And the line integral along here, f dot dr, is the same thing, but we're going to put in a pretty simple representation, x equals 0, y equals t, into this. And so what we get now is the double integral of 6 minus 1 we said, plus the line integral sine x of t plus y of t, right? This is f1 dx plus f2 dy. Replace dx with dx dt dt and y with dy dy dt dt. According to our first theorem for evaluating line integrals, this would have been difficult to do all the way around, but we can do it on this easy segment. Because dx dt is 0, right, making this whole first part 0, dy dt is 1, and y is 1, and sine is 0, so we have sine of 0 here. It's 0. And the line integral here is just the double, or the integral here is just the double integral of 5. The 5 can come out. We take the double integral of dA, that's just the area of the enclosed region, so that's 5 times the area, which, if you remember, it was just the region is just, can be broken up into 2 squares. Alright, here's a 9 by 9 square, here's half of a 9 by 9 square, and here's half of a 9 by 9 square. So we have 2 9 by 9 squares, twice 81 is 162, is the area of the region that's enclosed by the curve. So this first one becomes 5 times 162, and then to evaluate the integral t dt is just t squared over 2 from 0 to 27, gives us 27 squared over 2. When you add all these together, you get 2,349 over 2. It is the value of the line integral that we wanted. Here's a second application. Sometimes we have a multiply connected domain. Like, for instance, this one. We mentioned last time if you had a line integral that was this one, union some on the inside where the outside went counterclockwise and the inside ones went clockwise, so you're always keeping the region on your left as you travel along any of these curves. The line integral along the union of those regions, which is the sum of those line integrals along the individual curves, can be evaluated by Green's theorem, dg dx minus df dy, or df2 dx minus df1 dy, over the enclosed region between them. But then we said, well, here's the application, suppose these are all counterclockwise. Well, going counterclockwise, the line integral is just minus that going clockwise. So now Green's theorem for multiply connected regions says that the line integral along the boundaries where the regions on your left are added, and the line integrals where it's on your right, as you go around here, are subtracted, and all those together add up to the double integral over the enclosed region between them. Dg dx minus df dy. So let's try that now. Suppose we want to calculate this line integral, and we're given that this line integral happens to have value 4 pi, and this line integral happens to have value 5 pi, then we know that the line integral we want minus the 4 pi result minus the 5 pi result is equal to the double integral over this enclosed region. Now, if this is a circle of radius 5, I tried to mark it here, sorry for the oblong circle, and these are circles of radius 1, then the area of the region, well, to evaluate this integral, we said this is the double integral of dg dx minus df dy. Suppose we were given that 7, and so we want to take 7 times the area on the right-hand side. The area is pi times 5 squared for the outside circle, minus pi times 1 squared minus pi times 1 squared is 23 pi, right? Is the area of the region here. And so this, the double integral over the region of 7, is just 7 times 23 pi. And that added to the 4 pi and 5 pi put over on this side gives us the value of the line integral we want. 4 pi plus 5 pi plus 23 times 7 pi, there's a pi in there, gives you 170 pi for the value of our line integral. Alright, well, let's try a third object here. There's a vector form of Green's theorem that applies to flux. Flux, what's that? It's a way of measuring the area of fluid per unit time flowing through the boundary. It's used more in 3 dimensions than in 2 dimensions. That's the volume of fluid per unit time flowing through a surface. Let's do this in 2 dimensions and say the flux in 2 dimensions is the line integral along C bounding a region around a closed curve. The circle means closed curve. F dot n ds, where n is the unit normal of the curve. So if I have a curve like this, that's a simple closed curve bounding this region here going counterclockwise, and I take a unit normal at any point, and this is all going through a velocity field for the fluid, F. At this point, I can compute the component of F in the normal direction to the surface, right? So the component is, well, if this is a unit vector, the projection is just, remember, it reduces to F dot, the unit vector is the projection, right? The general projection onto V would be, onto U, well, V would be F dot V over length of V squared times V, but when V is a unit vector, n, then it's just F dot n over 1 times n, and if you leave off the n, then this is the length of the projection. So we have F dot n is the length of the projection of the velocity field onto a normal. It's the component of the flow field that's going out of the surface. Now if you integrate all along the curve, the component going out of this plane region, we call that the flux. And it's the area per unit time going out of the region, which can be negative. There's more coming in than going out. And this is, suppose we use unit outward normals, then if we want to evaluate this thing, we can actually use Green's theorem. I put the proof up here just for fun. I called this result a corollary because it's a theorem that follows quickly from Green's theorem, right? So a corollary is a theorem that follows quickly from another theorem. Here's the unit normal to a plane curve. We recall that x prime, y prime is the tangent vector to a plane curve. So what's a normal vector but y prime minus x prime, right? If you dot product this with the vector x prime, y prime, you get 0, right? X prime times this plus y prime times this gives 0. So this is perpendicular to the tangent vector, and then if you finagle a little of the plane, you can see it's actually the outward perpendicular vector, and then you divide it by its length. Length of r prime is the root sum square of x prime squared plus y prime squared. This gives you a unit outward normal. So here's how the unit outward normal is calculated. Now if you apply that with Green's theorem, the line integral f dot n ds can be evaluated as, well, f dot n, remember the theorem for scalar line integrals, the integral ds was integrand times length of r prime dt, integrated t going from a to b, the values that the parameter runs over. And now, if you take f equal little f, the vector field f to be little fi plus little gj, then this dot product f dot n becomes little f times y prime over length of r prime plus minus x prime times g. So that's the dot product, this vector with this vector, and is fy prime over length of r prime minus gx prime over length of r prime, and then times length of r prime dt. These r prime lengths cancel, and you just get integral over the values of the parameter fy prime minus gx prime. Well, this, if you recall by our theorem going backwards for evaluated line integrals, is f dy minus g dx. So the flux going through the surface, this curve here, is f dy minus g dx, but by Green's theorem, right, you take partial of this with respect to x minus partial of this with respect to y, and you get df, I'm sorry, this multiplies dy, take partial of this with respect to x minus partial of this with respect to y, that gives you df dx plus g dy, which is actually the two-dimensional divergence, right, of the vector field capital F equals little f I plus little gj. So what we have shown then is that the flux integral is equal to the double integral of the divergence of the velocity field f over this plane region that the curve encloses. So here it is, under the hypotheses of Green's theorem, the flux in 2D can be calculated by the line integral over c, I should put here, is the double integral over the region it encloses, divergence of f dA. So there's how you can calculate flux. It's a corollary of Green's theorem. Now we call this also the vector form of Green's theorem. Suppose we want to use this to evaluate the flux, the line integral along the curve f dot n ds through the curve c. So capital F, maybe in this case, is 3x plus y cubed. First component, 9y minus x to the fourth. Second component, suppose the curve is the circle of radius 2. Well, what we do first is we're going to parameterize this curve. We're going to say a circle of radius 2 has parameterization 2 cosine t for x, 2 sine t for y, and let t run from 0 to 2 pi to go around it once. So now, the double integral f dot n ds, the flux, by our theorem is, the single integral around the closed curve, is the double integral of the divergence of f over the region it encloses. But the divergence of this is pretty easy, right? The divergence is just a partial derivative of this with respect to x plus partial derivative of this with respect to y. It's del dot f, if you recall. So that's 3 plus 9. We just have to take the double integral of 12 over the region. Well, 12 comes out, and this is double integral. Life is never really this easy, but for these problems, we want them to be cooks, so we don't spend too much time doing double integrals. 12 times the area of the region we get, by virtue of it being a cook problem. Well, the area of the region is just pi r squared. It's a circle of radius 2. So it's pi times 2 squared, all times 12 is 48 pi is the flux for this curve here. All right, that's enough applications, pretty long section. I do want to point out that this actually has very interesting generalizations. We always want to generalize these things. The great Gauss, the prince of mathematics, said we must always seek to generalize. He spoke in German, I think, but he has an interesting story. Maybe you saw it in your textbook, how he was in grade school and was told by his teacher to add up the numbers 1 through 100. This teacher liked to assign long addition problems to teach them addition, but he had secret formulas he could use, of course. Well, Gauss knew the formula and wrote down 5,050 immediately. He was the only person in the class to get it right after the rest of the class slaved away the whole period. This kind of brilliance came up with a generalization of this thing we just did called the divergence theorem of Gauss. It says this: the double integral over a surface sigma that encloses a solid W. So this is the flux through a surface coming out of a volume. This is what you tend to use more in practice. What is the flux in 3 dimensions coming through a surface? Well, it's equal to the triple integral of the divergence of f dv. Look how that looks like what we had from the vector form of Green's theorem. It's just the 2 dimensions on this side, flux through a surface instead of out of a curve, equals a double integral instead of a single. You're just adding one more dimension. Equals a triple integral of the divergence over the volume enclosed instead of over the area over the region enclosed. So there's the divergence theorem of Gauss, a generalization of this part. And then how do we generalize the other part of Green's theorem? Line integral f dot dr equals double integral dg dx minus df dy. Well, it turns out that's a special case of this theorem. If instead of having C bound a plane curve, you allow this to be in 3 dimensions, and C goes along the boundary of the edge of a surface. Maybe you've got a big hemisphere here, and C is the boundary along the edge of the hemisphere, and you want to evaluate that. You can use the hemisphere, or whatever surface it is, whose boundary you go around here, and take the double integral over the surface, and instead of dg dx minus df dy, you're in 3 dimensions, you take curl f dot n ds. The double integral over the surface that's bounded by C is called Stokes' theorem, generalizes Green's theorem in this way. And if you take sigma to be a 2-dimensional flat region embedded in 3-dimensional space, this actually gives you Green's theorem as a special case. So you memorize Stokes' theorem, curl f dot n ds. That's the last chapter of the book. I kind of think of this as the crowning glory of calculus. You build up all this stuff, and this one is a really beautiful result that generalizes Green's theorem and takes into account all the things you've been doing, practically surface integrals and line integrals around a curve. And these are both generalizations of these things we just did, that integral f dot dr, which is also, recall, defined to be integral f dot t ds, the integral of the circulation, we call it, because your f dot t is the component of f tangent to the curve. So this is calculating the integral of the component tangent to the curve as you go around. Of course, it's called the circulation. How much are you being pushed around the curve? This one, the flux, is how much is going out. F dot n is the component of f. Again, think of f as a velocity field in both cases. Component going out. And so we call that the flux is the amount going out, and this is, and the circulation is the amount pushing you around. And these are its generalizations, the divergence theorem and Stokes' theorem. And then finally, let's see. wanted to show you this for fun. You can imagine, oops, wrong one. You can imagine trying to apply this in more dimensions. I don't know if there is a theorem, maybe there is. Here is a four-dimensional cube just for fun, sometimes called a tesseract. You can look this up on Wikipedia, it's a public domain picture. But this represents a translucent cube of 4 dimensions rotating through 3 dimensions, and so it's got cross sections that are little cubes. You can see them appearing and going around, and you can think about now how would you generalize some of these theorems to 4-dimensional cases.